Hello, my name is Oscar and I'll explain important properties of PID controllers. First of all, control elements are designed to act over an error signal, which is produced due to changes in the set point or by disturbances into the process, in order to generate an output control signal. That's why the main function of any controller is to keep the control variable near a desired value via its main objectives, which are minimize the steady-state error, minimize the settling time, and minimize the percent overshoot. Therefore, in a closed-loop system, the controller is an element that has as input the error signal, and yield an output that becomes the process input. In order to achieve so, the three principal types of control actions carried out by the controller are the proportional action, the integral action, and the derivative action. Specifically, the P controller gives an output which is proportional to the current error, and compares the set point value with the actual or feedback process value. Then, the resulting error is multiplied with proportional constant Kp to get the output. This proportional action of the controller can be described by equation number 1, in which Kp is a proportional constant, also called gain. However, if this gain value is set to high, then the output of the controller begins oscillating and become unstable, as seen in the graph, in which oscillations persist throughout time due to the high value of the gain, thus making the system unstable. For example, if we have a heater being controlled to give a set temperature, showed as the pink line in the graph, as the temperature approaches to the set point, the power supplied to the heater will be reduced, slowing down the heating process, so that in case of overshooting the set value, as seen in here, the temperature decreases and end up oscillating about the set point due to the action of the controller. That said, it is seen that the main effect of a P controller over the system is a decrease in the rise time and a decrease of the steady-state error, thus making the system more unstable. However, due to the presence of these controllers, the percent overshoot increases and we get some offsets in the system. Due to the limitations of the P controller, where there always exists an offset between the process variable and set point, an I controller is also needed as this provides the necessary action to eliminate the steady-state error by integrating the error over a period of time until the error value reaches 0 as established in equation 2, where Ki is an integral constant or controller gain. Therefore, due to the unique ability of this I controller to return the control variable back to the exact set point following a disturbance, both the proportional and integrative actions are associated in a PI controller. When both controllers are associated in a single control element, the output is given by the sum of the output equations for both individual controllers, stated in equation 3, in which Ki and Kp are proportional and integral constants respectively. Despite the advantages of the PI controllers regarding its simple structure, design, and low cost, this type of controller fails when the control object is highly nonlinear and uncertain. However, PI controller is useful as it will eliminate forced oscillations and steady-state error drastically, making it the most widely used controllers due to the overall improvement effect on the response when compared with the separate effect, as seen in this graph, in which both the proportional and integral controller effect on the response are drawn, as well as the whole effect of the PI controller over the system's response, showed by the red line. Moreover, PI controller will not increase the speed of response, which is expected since it doesn't have means to predict what will happen with the error in near future, problem that can be solved by introducing a derivative action. Since the I controller does not have the capability to predict the future behavior of error, it reacts normally once the set point is changed. However, the V controller overcomes this problem by anticipating future behavior of the error, since the derivative action yields an output of the controller that is proportional to the error's change rate, as stated in equation 5, where Kd is proportional constant, also known as controller gain. Therefore, as decontrollers are not used alone, they turn out to be particularly useful when associated with a PI controller. Finally, the PID controller has the advantages of each of the three individual controls actions, causing the output response to be described by the following expression, where Kp, Ki, and Kv are the proportional, integral, and derivative constant respectively. And if we were to draw this type of controller in a closed loop system, it would look like this. This type of controller is the most common control methodology to use in real applications, as the PID controller has all the necessary dynamics, such as fast reaction and change of the controller input given by the derivative action, an increase in control signal to lead error towards zero thanks to the integral action, and finally, a suitable action inside control error to eliminate oscillations with the proportional action, causing a similar output response as the one shown in the graph, which meet all these characteristics previously mentioned. Lastly, when comparing all P, PI, and PID controllers' effects on the system response included in both Tables 1 and Table 2, it is possible to identify the most important properties of features of these control strategies, as well as their effect on multiple parameters of a system response when implemented individually or associated, which also allows choosing the best control option according to the process variable. That said, it is possible to observe the effects on the parameters characteristic of a system and the effect that each AP controller, a PI controller, and PID controller have regarding the rise time, the overshoot, the settling time, the steady state error, and the stability.